Yeah, thanks for the introduction. Hello, everyone. I'm Haocong. I will be presenting our work, RowPress, Amplifying Disturbance in Modern DRAM chips. In this work, we demonstrate and analyze RowPress, a new redisturbance phenomenon that causes bit flips in real DRAM chips. We show that RowPress is different from RowHammer, demonstrate it in a real system with a user-level program, and provide effective solutions. Here's the outline of my talk, and I will start by some background in DRAM. DRAM is the prevalent technology for main memory. A DRAM cell stores 1 bit of information in a leaking capacitor, and DRAM cells are organized into DRAM rows. Redisturbance in DRAM has significant system-level implications because it breaks memory isolation. A prominent example of this is RowHammer, where repeatedly activating and closing a DRAM row many times causes bit flips in adjacent rows. RowHammer is the only studied redistributive fact, and various mitigations work by detecting high-row activation. This raises the following question. What if there's another redistributive phenomenon that does not rely on high-row activation? We find that RowPress is indeed such a phenomenon. So what is RowPress? RowPress is the redisturbance caused by keeping a DRAM row open for a long time, causing bit flips in adjacent rows. These bit flips do not require many row activations, and we find in some cases only one activation is enough. Now let's see how this is different from RowHammer. Instead of high activation count, RowPress increases the time that the aggressor row stays open. Doing so disturbs adjacent rows enough to cause bit flips without a very high activation. We even observe bit flips with only one activation in extreme cases. Now let's take a look at our detailed characterization of RowPress. The two most important takeaways from our characterization results are: first, RowPress significantly amplifies DRAM's vulnerability to redisturbance. Second, it is different from RowHammer. Now let's see how we get to these conclusions. I will start with our characterization methodology. Use an FPGA-based DDR4 testing infrastructure developed from DRAM Bandit, which gives us fine-grained control over DRAM command, timing, and temperature. We test 164 DDR4 chips from all 3 major DRAM manufacturers, covering different die densities and die revisions. The key metric we are looking at here is the minimum number of aggressor activations needed to induce at least 1 bit flip, or AC-min. We use a single-sided RowPress pattern, as shown in the figure, where we only activate one single aggressor. We sweep the aggressor row on time from 36 nanoseconds to 30 milliseconds. We use a checkerboard data pattern, and unless otherwise specified, we test the DRAM chips at 50 degrees Celsius. We use a bisection-based algorithm to search for AC-min, and we cap each search iteration at 60 milliseconds, which is strictly smaller than the refresh window to avoid seeing any undesired retention failures. This is enough to explain our results that are going to be shown in the presentation, and we have many more sensitivity studies in the field. Next, let's see the key characteristics of RowPress. I've already shown these 2 key takeaways. Now let's see some details. RowPress amplifies redisturbance in DRAM because it reduces the minimum number of activations needed to induce a bit flip by 1 to 2 orders of magnitude. In extreme cases, only one activation causes bit flips. RowPress also gets worse as temperature increases. RowPress is different from RowHammer because it affects a different set of cells and behaves differently as access pattern temperature changes compared to RowHammer. Now let's see some detailed characterization results to understand how RowPress amplifies redisturbance. First, we look at how the minimum number of activations needed to induce a bit flip, or AC-min, changes as aggressor runtime increases. We show AC-min on the y-axis and aggressor runtime on the x-axis, both in log scale, of a representative die revision from manufacturer S. Each data point here shows the average AC-min value across all DRAM rows we test, and the error band shows the minimum and maximum AC-min values we observe. When aggressor runtime is 36 nanoseconds, our access pattern is identical to RowHammer, and as we increase aggressor runtime, we start to see the effect of RowPress. We highlight 2 potential upper bounds of aggressor runtime according to the data extended on the x-axis, which are the refresh interval and 9 time zone. We also highlight AC-min equals 1 on the y-axis. We observe that as aggressor runtime increases, AC-min significantly reduces, and in extreme cases, only one activation causes bit flips. We observe the same trend for all dies we test from manufacturer S, and the same holds for almost all die revisions from all three major DRAM manufacturers. We observe that as aggressor runtime increases from 36 nanosecond to 7.8 microsecond, async reduces by 21x on average across almost all die revisions from all three major manufacturers. When aggressor runtime increases to 70.2 microsecond, async reduces by 191x on average. We conclude RowPress significantly reduces the minimum activation count to induce a bit flip as aggressor runtime increases. Next, we investigate RowPress at a higher temperature by looking at async at 80 degrees Celsius, normalize that at 50 degrees Celsius, which we show on the y-axis. We observe that as aggressor runtime increases, RowPress requires significantly fewer activations to cause bit flips at 80 degrees Celsius compared to 50 degrees Celsius. We conclude RowPress gets worse as temperature increases. Next, let's see in detail how RowPress differs from RowHammer. We first look at this relationship between the cells vulnerable to RowPress to those vulnerable to RowHammer. We define the cells vulnerable to RowPress or RowHammer by those experiencing bit flips with the minimum activation. We define the overlap between the cells vulnerable to RowPress and RowHammer as the number of cells vulnerable to both RowPress and RowHammer over the number of cells only vulnerable to RowPress. We show such overlap on the y-axis. We observe as aggressor runtime increases, and only a negligible amount of cells vulnerable to RowPress are also vulnerable to RowHammer. We conclude most cells vulnerable to RowPress are not vulnerable to RowHammer. We also look at the directionality of RowHammer bit flips versus RowPress bit flips, and we find that they have opposite directions. We also find that as aggressor runtime increases beyond a certain level, single-sided RowPress becomes more effective at inducing bit flips, or in other words, it requires fewer activations to induce bit flips compared to a double-sided RowPress pattern. This is very different from RowHammer, where a double-sided RowHammer is strictly more effective at inducing bit flips compared to single-sided. I've already showed that RowPress gets worse as temperature increases. This is also very different from RowHammer. Now let's see our real system demonstration of RowPress. We demonstrate RowPress in a system with a recent Intel processor and a Samsung DDR4 module that already has TR RowHammer mitigation. The key idea of our RowPress program is to keep a DRAM row open for a longer period of time by keeping on accessing different cache blocks in the same row. Here's the key part of our program, where we can change the number of cache blocks read per aggressor activation. Note that if we only access one cache block per aggressor activation, our program does the same as RowHammer. We run the program on 1,500 arbitrarily selected victim rows, and we show the total number of bit flips as we change the number of cache blocks accessed per aggressor activation on the left, and the total number of rows that has bit flips on the right. We conclude that leveraging RowPress, our user-level program induces bit flips when RowHammer can. Now let's see how to mitigate RowPress. We propose a methodology to adapt existing RowHammer mitigations to also mitigate RowPress. The key idea is based on the characterization results. We first limit the maximum time that a DRAM row can stay open in the memory controller to strike a balance between row buffer locality and the read disturbance caused by RowPress. The second, we configure the RowHammer mitigation to account for the RowPress-induced reduction in the minimum activation count needed to cause bit flips. We evaluate our methodology on two existing RowHammer mitigations, Rethinking and Para, using RAMulator. The key metric we are looking at is the additional performance overhead of the adapted mitigations over the original ones. Our evaluations results show that we can mitigate RowPress at low additional performance overhead. Now let me conclude my talk. In this work, we demonstrate and analyze RowPress, a widespread read disturbance phenomenon that causes bit flips in real DRAM chips. We characterize RowPress on DRAM chips from all three major DRAM manufacturers, and we find that first, RowPress greatly amplifies read disturbance by reducing the minimum activation count needed to cause bit flips by 1 to 2 orders of magnitude, and in extreme cases, only one activation gives you bit flips. Second, RowPress has a different mechanism compared to RowHammer. We demonstrate RowPress in a real system with a user-level program that can induce bit flips when RowHammer can. We provide effective solutions to mitigate RowPress at low additional performance. We have many more results and analysis in our paper, and our work is fully open source and artifact evaluated. Thank you for your attention, and I'm happy to take any questions. Okay.
Questions?
Was it just me, or did they say the average improvement was negative? Like the average performance penalty was negative?
That's because we evaluate multi-program workloads, and the metric is greater speed up, and because we limit the maximum time that the VMware can stay open, it improves the fairness in some workloads.
Okay.
So that costs the average slowdown to be negative.
Okay.
Moin Qureshi, Georgia Tech. Very nice talk. A quick question for you. For regular workloads, what's the maximum time you saw that the row was open for the baseline?
We have some input tests, and I think the average number is about 1500 nanosecond to 1800 nanosecond for some workloads in spec 2008.
Great. So for 1 to 2 microseconds, if you keep the row open, what's the impact on both ends? Is it like 5% reduction in activation time?
For 1 to 2 microseconds, it could reduce. I don't have an exact number in my mind now, but the reduction should be large.
Even for 2 microseconds?
Yes, 2 microseconds.
Thanks.
Hi, nice talk. I'm Irina from Apple. A few questions. First is, what causes RowPress?
So while our paper is under review, there are a concurrent work put on by some engineers. They basically explains there's a device level effect called passing wave effect that attracts electrons from the victim cells. So and this effect is very significant when you keep the aggressor open for a long time. And we believe that could be one of the device level mechanisms to cause these kind of things.
Okay, and have you evaluated this in ECC-based DRAMs, like DRAMs with in DRAM ECC?
No, currently our infrastructure only supports GDDR4, but we are working on evaluating this effect in DRAMs with on the ECC like GDDR5.
So do you expect the severity to significantly reduce with in DRAM ECC-based DRAMs?
So from the circuit level, we believe it might only get worse because the technology continues to scale down. But if we add the effect of on the ECC, if we want to predict like the bit flips with ECC, I'm afraid I cannot say before we finish all the experiments.
Okay, thank you.
Hi, Kevin Laughlin, University of Michigan. Awesome work. I was wondering, are you referring it to the phenomenon as read disturbance because it only works if you trigger the activation from a read? Or could it also work as a write disturbance effect? Because you can get the activation either way. And I believe, but potentially I'm wrong here, that RowHammer could work with either reads or writes. And so I'm wondering if RowPress is different.
Yes, so the operation that matters is the activation of the row. Yeah, I agree that both, let's say from a systems perspective, both read and write can trigger activation. So write can also work, but yeah, we use the term read disturbance because it's kind of like a legacy term from RowHammer times that we can read disturbance.
Let's thank the speaker again, please. Thank you so much.